Hello, everybody. Today, I just wanted to give you a brief rundown of stars and stellar evolution. This lecture is something that's going to be really tough for me because this is my bread and butter. This is something that inspired me to start teaching this subject specifically. Um, and so I'm really passionate about it, but I'm going to try to condense this lecture down into as small time frame as possible because I know you have other things that you need to do. But if you would just please follow along with me, I'll try to go through and talk about what stars do, how they end up to where they end up, and of course how we classify them, how we organize things. So let's go ahead and get started and talk about star formation. So stars start, all stars start as the same thing, a nebula. A nebula is just a big cloud of gas and dust in the universe. Stars are born in a nebula. And it all has to do with gravity. Gravity will collect those particles of gas and dust and start to condense them. As the object gets larger, it has more gravity as it pulls more things in. And so as it gets, it's kind of like a feedback loop. As it gets larger, it has more gravity, it crunches down. As it crunches down, it has more gravity, it pulls more things in, crunches down more. So as more and more particles come together, the mass of gas and dust starts to grow. The picture that you see here is actually something that was taken from by the Hubble. It's called the Pillars of Creation. Inside of this big, huge cloud, you can see these dark areas. There are stars that are collecting uh, under the intense pressure of gravity to form and start to glow as new stars. So as gravity pulls more and more of this gas and dust together, the nebula will start to shrink. Um, and now it has to do with the law of conservation of momentum. As it shrinks down, any kind of motion that's in the gas is going to be exaggerated. And so it's going to start to rotate. As it rotates, it's just like a pottery wheel. It starts to flatten out to a disk. This is called a protostar. It's right before the star begins to glow. Now, the one thing that I want you to pull away from this is that it all has to do with the amount of matter. The the evolution or the life cycle of the star has to do with the amount of mass in that original nebula. If it's very, very massive, then it's going to determine what the star is going to act like throughout its life, how hot it's going to glow, its brightness, its luminosity, its radius, its temperature. If there's not a lot of mass in that original nebula, then you may not get through all of those stages. You may only get to the protostar stage. And you end up with something called a brown dwarf, which is just an object that's extremely dense but doesn't have enough mass to undergo nuclear fusion, and so you don't have the typical star giving off light. But if there is enough mass, um, that protostar will start to glow as nuclear fusion begins in its core, which is around 10 million degrees Celsius. At this point, it enters what's called the main sequence. This is where hydrogen is being fused into helium in its core, and it starts to give off light. Once this happens, we have your typical star. And this object could last in this main sequence state for billions of years. But if it's really, really massive, it may only last 100 million years on the most massive star. So again, it all has to do with mass. The main sequence stage, where it's fusing hydrogen and helium, is going to be the longest stage of a star. Um, as it coalesced out of that nebula and starts to undergo nuclear fusion, um, again, it's dependent on mass. If it's really, really, really massive, then it will be a blue-white, very bright star. If it's a lower mass, it could be a red star, or like our sun, which is a small to medium mass star. It'll glow as a yellow star, class G. So a star with about the same mass as our sun will be in this stage, the main sequence stage, for approximately 10 billion years or so. But more massive, less time. Less massive, more time. It could glow for tens of millions of years, tens of billions of years, excuse me. But again, it all has to do with mass. The more massive it is, it's going to determine how it's going to live, how fast it's going to stay in that main sequence. Very, very massive stars are kind of like race cars. They burn through their hydrogen very, very, very quickly, um, and will burn hotter. Lower mass stars will burn much cooler, and it's kind of like a Prius. It'll burn for uh, billions of years. But again, it all has to do with mass. When small to medium mass stars use up all of that hydrogen in the core, it starts its third stage of life as a giant star. Um, a giant star is a very large, bright star whose core has used up almost all of its hydrogen. As a main sequence star, you've got two things happening. You've got gravity trying to crunch everything down, but you also have the fusion reaction trying to blow everything up. And so a main sequence star is balanced. Those two forces are balanced. When the hydrogen is used up in the core, gravity wins. And so gravity will crunch down the core and it'll heat up. As this core heats up, it causes the outer envelope of the star to expand outwards into space and become a giant star. The atmosphere will cool, so it'll go from, for example, our sun will go from a yellow star to a red giant. Much cooler surface temperature, but much, much larger. As a matter of fact, when the sun reaches this point, it'll probably expand out into the Earth's orbit. And of course, Mercury, Venus, the Earth will become part of the sun's atmosphere at this point. In really massive stars, they become even larger. So they'll go through their main sequence much faster. Um, Again, the core will shrink down and heat up. This will cause the outer envelope of the star to expand, but even much, much, much larger than what our sun will end up as. So in a super giant star, it could be the size of Jupiter's orbit. So we're talking massive, massive star. But again, cooler on the outside, so it's going to be a red supergiant. So as the star expands, the outer gases of the star will cool and some will start to drift out into space because they're no longer held by gravity. Um, what this creates is something called a planetary nebula. It could glow for millions of years from the energy of that core, heating those gas particles up as they slough off into space. This is kind of the end stage of a planet like of a system like our sun. The core will be left behind though. The core is then called a white dwarf. So it's the core of that original star. It's extremely massive in a very small space. So we're talking the size of a state, this object, but extremely hot, and that's why it's white, because it burns at such a hot temperature. But it is not fusing. It is just that leftover heat from that core. White dwarfs can shine for billions of years, and eventually they will cool off into something called a black dwarf. Um, but it could take hundreds of billions of years to get there. I'm not even sure if black dwarfs have been directly observed to this point, just because they take so incredibly long to cool off. But in high mass stars, something very interesting will happen. So these are stars with much more mass than the sun. Um, in a main sequence star, that balance of gravity and fusion um, is maintained. When the core of a supermassive star or a high mass star, when it runs out of that material and gravity crunches the core down, it can create a shock wave. As it burns through hydrogen to helium, it'll shrink down. From helium to carbon and oxygen, it'll shrink down and heat up even more. Once it uses up all of its nuclear fuel in the core, the gravity wins. And so the star clamps down and then the shock wave rebounds it back out. That's what this diagram is showing. This shock wave causes elements within the star to hit each other with such force that they will fuse into other elements beyond iron. So in these really massive, supermassive stars, for example, for stars after the Big Bang, they will create all of the elements beyond number 26. Iron is a very special element, so when the core of a star reaches that stage, fusion can no longer be maintained. And so Gravity wins, crunches down. If you've ever seen a basketball in slow motion, when it hits the ground and it deforms and then rebounds back out, that's kind of what I envision the core is doing. It crunches down, and then the shock wave causes all those elements to bang into each other with such force that it fuses to create all of those heavier elements beyond number 26, beyond iron. What's left behind, other than a planetary nebula, this huge nebula of material that's going outwards into space? Um, but what's left behind in massive stars could be something called a neutron star. These objects are so exotic. They contain more mass than the sun, but in objects with a radius of about 10 to 15 kilometers. We're talking very small, but very massive. So the density of these objects is incredible. It is so dense, in fact, that the only types of particles that can exist in this state are neutrons. And I think the analogy is if you had a teaspoonful of neutron star material here on Earth, it would weigh as much as a mountain. That's a lot of matter in a very, very small space. But again, it has to do with mass. The more massive the nebula, the more massive the star, um, the more exotic the end result, the end of the life cycle will be. Speaking of exotic, there are types of neutron stars called pulsars. Now, as the core is being shrunk down, of course, it will spin faster and faster due to the law of conservation of momentum. Sometimes the pole of those neutron stars can focus towards the Earth. When that happens, astronomers will actually pick up a radio wave, um, just a radiation beam from the pole of that star. And what's really cool about pulsars is they pulse with such a regular repeating pattern as they spin around. We actually use them as clocks. So on this website that I've included, you can actually listen to those pulses. For example, this pulsar, uh, which repeats its pattern every zero point 0.7 seconds. So each pulse is when it's pointed towards the Earth and giving us a little beep. Some are faster, some are slower, but they all produce this regular pattern. This one is extremely fast. So anyway, you can explore those if you like. But again, a pulsar is just a neutron star that as it spins, it sends a beam of radiation towards the Earth, which we pick up with satellites. The most massive nebulas end up as the fastest burning stars, the blues and the blue whites. Um, they burn through their nuclear fuel very quickly. And in these massive beasts, which could be 20 times the mass of the sun, can produce leftovers that cannot form into neutron stars. They actually form into black holes. Now, black holes I could spend a whole lesson on, but here's the basics of it. To get away from a very small object, you have to attain a very small speed. It's a concept called escape velocity. So if you were standing on an asteroid, let's say that was 5 kilometers in diameter, not very massive, you could actually achieve escape velocity just by jumping. And so you would jump away from it and you would escape it, never come back. You're completely escape its gravitational pull. For an object like the moon, you have to be going a couple of thousand miles per hour in order to be fast enough to get away from its gravity completely. For the Earth, that speed is about 17,000 miles per hour. As you move up in mass, so does your escape velocity. Well, black holes are so massive in such a small space that the escape velocity, the speed required to get away from it, is greater than 186,000 miles per second. That is the speed of light. And so these objects have such a strong gravitational pull. They're small. They're, 10 to 15 kilometers, 30 kilometers. They're not very big, the size of a city. But there's so much matter contained in such a small space that its gravitational pull is incredible, such that the escape velocity to get away from these is more than the speed of light, which basically means they don't shine. They don't give off visible light. They look like just nothing. They don't give off infrared because infrared, uh, you know, uh, is heat, and we can't see the heat coming off this object because, again, greater than the speed of light. No light is emitted. Um, so these are strange, exotic objects. But again, they are the remnants, the cores of these stars that were really, really, really supermassive, 20 times more massive than the sun. Um, Black holes aren't vacuums. They don't suck everything in. But if an object gets within that gravitational pull, it will start to fall in, just like any other object. Um, you can have objects orbiting black holes. You can have other stars that orbit black holes. You can have planets orbiting black holes, but they are not these huge vacuums that you may see out in science fiction. So here's the recap. And again, the one thing that I want you to understand is that the life cycle of a star is dependent on its mass. If it is a low mass nebula, it will form that protostar. It may not even make it beyond that. It may just end up as as a brown dwarf. But if it has enough and achieves nuclear fusion, it becomes a main sequence star. Over time, after the nuclear fusion fuel has run out, after the hydrogen has run out in the core, the outer layers will escape into space, and you're left with the core of that star, which is now a white dwarf, which can, of course, cool into a black dwarf. In an average mass star, like our sun, we go from that nebula to the protostar to the main sequence, balancing fusion with gravity, which will eventually heat up after it uses up all its fuel in the core, causing the outer layers of the star to expand into a red giant. The outer layers will slough off into space as a planetary nebula, and what's left behind is the white dwarf, which will eventually cool into a black dwarf. But in the most massive nebulas, in the highest mass nebulas, they will become these hot, large main sequence stars, blue, white, which will eventually use up all its nuclear fuel in the core, expand to become a red giant or a supergiant, which can then go supernova. And the core that's left behind can be a neutron star, or if it's massive enough, a black hole. Again, all to do with mass. So a star goes through different properties, and it's directly related to its age. Its color, its size, its temperature, its brightness or luminosity is all directly related to its age. And how quickly it moves through those properties and goes through those properties is all dependent on mass. So how do they change over time? How do those properties, color, size, temperature, change throughout its life cycle? If we look at low mass stars, its color will go from like a red yellow star to a red giant as it gets larger into a white dwarf. But in the most massive stars, they could go from a blue main sequence star to a red supergiant to a supernova explosion, which can outshine an entire galaxy, um, to a neutron star or black hole. So the properties will change as it evolves and goes through its life cycle. So how do we classify stars? How do we group them? And that brings us to something called the HR diagram, the Hertzsprung-Russell diagram. Imagine an alien civilization trying to classify humans. They'd look at and take a selection of a bunch of humans and look at where they are, and what they can do. So, babies crawl on all fours, adults can walk on two legs, and then old people walk on three with a cane or whatever. And they could put them on a nice chart to classify and then look at how we evolve through time. Same thing has been done with stars. The HR diagram actually classifies stars based on temperature and brightness or luminosity. And when you take a big sample of all the stars out there and you put them on this graph, you can see these groupings. The main sequence, which actually is about 90% of all stars, are in the main sequence stage, so burning hydrogen into helium. You have this small collection of not very bright, but really hot white dwarfs, the end stages of um, low mass and medium mass stars. Then you have your red giants over here, which are very bright, but not very hot at all, which are actually the remnants of low and medium mass stars. And then, of course, your supergiants, which are pretty hot, but also very, very bright, which are the remnants of these very high mass stars after they have left the main sequence. And so what we're going to do in the next activity is you're going to be classifying stars and looking at patterns that come into these diagrams and how it allows us to look at the life cycle of stars. So if you would, please move on to the assignment for today for the HR diagram gizmo. You just complete the accompanying sheet with that and submit. Again, so sorry to have talked so fast. I know I probably left a lot of you, and I really, really apologize, but I encourage you, go out, look at some of this material, go out, do your own research. There is such a wealth of information out there. Um, and if you have any questions, please let me know. Thank you so much.